Number 1, the element with the largest change in oxidation state. So we've listed out some of the oxidation state, and if we do a comparison, we can see that for option B, chlorine has actually changed for 5 units when it goes from 0 to +5. So this is the largest change we can have for all the other options if you have listed out all your oxidation numbers correctly. Okay, change of 5 units. Number 2, we have an isotope and they tell us that 1 electron combines with 1 proton, and then they combine to form a neutron. So if we were to list out all the protons, neutrons, electrons for this atom, and then we will combine an electron with a proton, so we end up with 1 proton less, an electron less than before, and 1 more proton than before. So this is the before, this is the after, and then if you compare the 4 options, C, we have 37 neutrons in the new atom. Boron hydride, boron trifluoride. So we have BH4- and BF3. If you do the dot and cross diagram, we will have BH4- to be a tetrahedral shape, 4 bond pairs, no lone pair. BF, 3 bond pairs, no lone pair. So this will be trigonal planar. Number 4, we have the energy change here, +180, and then we have to use it to find out what is the bond energy of NO. From the data booklet, we have the nitrogen energy and the oxygen energy. So what we do is we use bond energy of reactants minus bond energy of products. And then one thing that might be different from the current data booklet you're using is the bond energy of nitrogen. Right? In 2012, the data given was 994. Whereas in the recent editions, it seems to be 944. So that might give us an answer that's different from any of the options here. So if you use the data given in 2012, we have 994 plus 496. That's for oxygen. Subtract 2 times of nitrogen oxides. Overall, that will give us 180. And from here, you have a simple equation where you solve for your bond energy of nitrogen oxides. That will give us 655. If you use 944, you will have a number that's close to 655, but not 655 exactly. So best option if you have to use will be choose the closest option after all. Number 5, what are the energy changes for atomization, formation, solution? Atomization is always overcoming attraction force, changing things into gaseous atoms and all that, breaking bonds. So it will always be endothermic. Formation depends on the comparison between products and reactants, the energy level. It could be exo, it could be endothermic. You can't tell which is it. So that gives us option B. Solution also, it depends on the attraction between the solid before they are dissolved and the attraction between the solid and the solvent when they get dissolved. So it could be exothermic, it could be endothermic also. Number 6, what is the mass of ammonia measured at this temperature and giving this volume? So what we have to do is we have to use the gas equation, or ideal gas equation, to find out the number of moles. We change the pressure to kilopascal, volume to cubic meter, temperature to kelvins. Gas constant 8.31. Once we put in all these numbers, we have the number of moles to be 0.2 moles. We have 0.2 moles of ammonia. We multiply by the MR, we will have the mass of ammonia. Number 7, extracting magnesium. That's similar to extracting aluminium from aluminium oxide. So the general idea is at the anode will involve anions, which will involve oxidation. Cathode will involve cations that will be reduced. So since they're all talking about magnesium, we will be focusing on the cations and then the cathode. And then magnesium 2 plus becoming magnesium metal will be reduction. So magnesium ions travel to the cathode and are reduced. Number 8, structure of silicon dioxide. So understand that silicon dioxide is a giant covalent, something like diamond structure. So we have our silicon here. It is joined to 4 other oxygen, and each oxygen is joined to 2 other silicon. So and is of course a covalent bonds, giant covalent bond. So if we have covalent bonds, that might be the easier one to sort out. And understand that 1 silicon to 4 oxygen, 1 oxygen to 2 silicon. Number 9, Dalton's idea of an atom. So what prediction is still considered correct? Okay. All atoms are still very small in size as predicted last time. If you look at the other options, all atoms have the same mass. If you are the same element, that's not necessarily true because we can have isotopes. They have different mass, but they are the same element. Option C, all atoms are different in mass from other elements. If we can use isotopes of sodium and magnesium, they can have the same mass, but they not necessarily are the same elements. No atoms can be split. We have atoms that can be split into protons, neutrons, or other small particles. So B, C, D are no longer valid. Number 10, calculating enthalpy change of formation using values of combustion. So we write out the energy change in formation for ethane based on their elements, calculated to be -158, and in general, combustion of reactants minus combustion of products, that will give us the heat of reaction. And then we put in all the numbers. This is the heat of reaction, 2 times combustion of carbon, because there's 2 here. This is the number we need to find out. Add to 3 times the combustion of hydrogen, 286, and subtract heat of combustion of our products, which is our ethane, 1560. And then we solve for the unknown, that is heat of combustion of carbon. That will give us 430. Okay, so this is the value used to allow us to get -158 at the end. Which process could be used to calculate the bond energy? By dividing the energy change by n. They all look pretty unfamiliar because they are in terms of unknowns, but first thing you can look out for is A is purely bond breaking. B, we have bond breaking and then bond forming of molecules at the other side. C, we also have bond forming at the end. So do we have for D, that's bond forming. So A is the most likely choice, where it involves purely bond breaking into its atoms. If it's unfamiliar, you can compare to things like methane, where we break methane's bond, we have C and 4 hydrogen, and if we want to find the bond energy of a CH bond in this case, we have to take this amount divided by 4, because there are 4 CH bonds inside here. So if we do a comparison, we are breaking n number of XY bond, so we take this value, energy change for this whole reaction, divide by the number of bonds broken. Number 12 involves being familiar with the shapes of molecule based on their lone pairs and bond pairs. So I have drawn them all out here for comparison. Water, bent, carbon dioxide linear. Water bent, sulfur dichloride also is bent. So B is our answer. We can check the rest. Ammonia has one lone pair, so is trigonal pyramidal. BH3, no lone pairs, is trigonal planar. Silicon dichloride mentioned was bent, and BeCl2, no lone pairs, will be linear. So number 12, water and SCl2 are the same shape.